Check, check. Hello, everybody. Thank you for coming to our next talk, Hacking on the Nanoscale, Dual Beam Devices for Rapid Prototyping and Reverse Engineering. So if you could, please give a round of applause for our speaker, Lorenz.
Thanks a lot, and thanks a lot for showing up here. I'm going to take you on a little journey to the world of dwarfs, or gnomes in English. So I will talk about a new kind of tool that we use in nanoscience, and hopefully we find out, thanks a lot, hopefully we find out how this can be applied to security issues. So what the hell is this talk going to be about? I will do it in a conventional way, so I will first give some background and motivation. I will talk about the basics, so that might be a bit lengthy, but I hope you stay through it. I will show you the actual device, and I will talk about applications like reverse engineering, rapid prototyping, and circuit modification. I will... Closer? Okay. I will give a brief summary, and I have a question in the end that I hope I will get some answers from the audience. So why do I actually give this talk? A great physicist, Richard Feynman, once said, "I believe that we must attack these things in which we do not believe." 2 years ago at the conference in Berlin, the motto was of the keynote, "We lost the war." I actually don't think so. I think we are in an arms race, and although lots of things are playing against us, we might be able to use technology to turn the things a little bit. Briefly to my background, I've been studying physics in Germany, in Regensburg. I've done some research in the States, and since 2005 I'm at the Low Temperature Laboratory in Helsinki, Finland. And as a side job to doing my thesis, I got nominated the FIB expert for this Micronova Center for Micro and Nanofabrication. So that it is called an expert just means that I'm their expert and not necessarily that I am an expert. What I'm definitely not is I'm not a security or computer guy. I know how to turn it on, and I know maybe a bit more, but for the question we have in the end, I need your help. So, what the hell is it all about? It's about nanotechnology. Most of you might have heard about nanotechnology. It's small robots that can swim through your bloodstream and take out these nasty allergens, and they can repair your blood cells, and if things go really bad, they will take over the world and turn everything in a grey goo. At least that's what some people say. It's of course bullshit. So, what is nanotechnology actually about? We are dealing with two phenomena. The one is called top-down, which is we have started with the microprocessors and other devices. We've started to just shrink the size of the devices to a level that we are actually, since some years now, below the 100 nanometer scale, and we can really claim that we are doing nanotechnology. Another approach that I'm not going to talk about is the bottom-up approach, that people are trying to build machines, devices, something up by self-assembly or by the same means that nature uses. So, but I will focus on material science and electronics. So how does this whole nanoscience work? Of course, whenever you do something like engineering or science, you need a sort of toolbox. The toolbox of nanoscientists are, for one hand, microscopes. This is a state-of-the-art scanning electron microscope. We have different sorts of microscopes that were developed in the 80s, scanning probe microscopes, where you actually have a very fine tip that with which you can scan a surface and basically achieve atomic resolution. So, in addition to that, we need some facilities. In most cases, we have to work in clean rooms because our structures are very small, so even dust particles in the air could seriously destroy our structures. And another thing, especially if you deal with electronics in very small structures, you have problems with heat, and that's why we use elaborate systems for cooling down our experiments. In this case, you see a refrigerator that cools basically down to almost absolute zero. So this is not necessary for all the nanoscale experiments, but whenever you shrink things down, thermal vibration, thermal noise becomes a problem. So the system I'm going to talk about is some chimera consists of a scanning electron microscope and a focused ion beam. If you put these together, you get these shiny devices, and if you buy them with FEI, they are called a dual beam system. If you buy them with ZEISS, they are called a cross beam, but the principle is the same. You have two columns that deliver two different ways of imaging. In order to kind of get to what we can do with these systems, I would like to give you a bit of the basic principles of how a scanning electron microscope works. Here, this is pretty new, that was released this year. So whenever you thought that a scanning electron microscope has to be something really big and expensive, these devices actually fit on a tabletop. They are about the size of a very small fridge, and they are just slightly more expensive than a car. So even though you cannot see it here anymore because everything is so neatly integrated, the system is pretty much the same since years. On the top you have an electron gun that in most cases is just a very fine needle. You heat it up and electrons come out. Given that you have this whole thing enclosed in some sort of vacuum, otherwise the electrons would just stop pretty quickly. Like in a light microscope, you have a lens system that transforms and focuses your beam that you get from the gun. The difference between a scanning electron microscope and a light microscope is that you actually create a very tiny beam that is focused on the sample, and then you use these scanning coils to move the beam around on the surface, scan the surface. And while you scan the surface, you collect the electrons that come out of the sample with a small detector in the chamber close to the sample. And if you take the signal, the XY signal from the scanning coils for deflecting here or for the XY position on the screen, you can, if you record the current you get from each point of the sample, you can get a nice image. So how does this image look, and is there a little bit more to the image than is obvious? It depends a bit on how you actually collect the electrons that come out of the sample. So if you look here, you have some incident beam of electrons that hits at some point the sample. It's very small, but unfortunately the electrons are not stopped immediately, but they kind of continue on and cause several different effects. I will not go into detail too much. You have light coming out, you have X-ray radiation, You have electrons, if you have a thin sample, you have electrons that just go through. Some go through without even noticing that there's a specimen, others get deflected. But for the case of the scanning electron microscope, the interesting parts are backscattered electrons and secondary electrons. So backscattered electrons, this is an electron coming from the beam that gets reflected by the material. If you look at those, you get a nice map of the elemental composition of the specimen you're looking at. If you look at the secondary electrons that are created by the incident beam that just kicks out other electrons, then you get an image with more surface information. The focused ion beam is pretty much the same. Instead of electron source, you have a liquid metal. In most cases, it's gallium. You have a small metal tip, and if you heat up the gallium slightly, it forms some small or some thin film, and given that you have extraction voltage, it just sprays off the tip of the needle. So once you have this gallium ions coming out of this tip, you can do the same as you did in the electron microscope. You send them through a lens system. You have again some sort of deflection mechanism that scans your beam over the sample. And the beam, in a similar way like the electrons, creates secondary electrons that come flying out, and you can detect those. So you can use the FIB, the focused ion beam, for imaging. This is pretty straightforward. If you have a very low dose, you get some nice signal. Basically looks like an electron microscope picture. Here we have some metal lines and nothing much different than an electron picture. There's only one effect. If you look at metals that have some granular structure, even though the metal itself is flat, you see all these small islands. This is because the metal lattice is oriented differently in the grains of the metal, and you get some channeling effects. So that kind of reduces your secondary electrons. And this, although the surface is flat, it looks structured in the picture. What else can we do with the FIB? Just watching would be boring, but we can, if we